Thank you for being here today. So I'm going to, as Dr. Schultz mentioned, talk to you about my research that I've conducted. It is entitled Utilizing LiDAR Data to Analyze Access Management Criteria in Utah. So I'm going to start out talking about the purpose and need of this research, then explain what access management is, and a little bit about what LiDAR data is. Then I will describe and show you the data sets that I utilized in this research, talk about the initial correlation and hotspots that we found, an automated Excel workbook that we used in our research to conduct two analyses, access category criteria analysis and a before-after raised median analysis. So the purpose of this research is to utilize the LiDAR data to do a safety analysis of the state. Looking specifically at driveways and raised medians. So we were going to determine hotspot locations where we could implement access management techniques and then utilize a hierarchical Bayesian statistical analysis on raised medians to see how raised medians affect the safety of a roadway. So what is access management? Access management is the coordinated planning, regulation, and design of access between roadways and land development. So basically, access management is a way to reduce conflicts on a roadway and improve safety. And this can be done through a variety of techniques, including driveway consolidation, median treatments, and left turn lanes. But this picture has many more techniques that can be used, such as adding bike lanes and pedestrian amenities. Utah has access management guidelines. They were published in 2013. So our administrative rule R930-6 is what it's called. And these guidelines are meant to maximize public safety and protect the state highway system. So there are 10 categories as shown in this table. And these categories are separated based on the posted speed limit, variety of spacing for intersections and driveways, whether it's of urban or rural design, and functional class. And so looking at this table, category 1 is a freeway or interstate, which should have 0 access. But as you increase the category to about an access category 8, you increase access as you increase your category. So there are different regulations on driveway spacing and the number of accesses that you can have per mile on the roadway. LiDAR data was what we used in this research. LiDAR stands for light detection and ranging. And how you collect LiDAR data, you have your collection equipment, and it emits laser pulses constantly. And these laser pulses, once they leave your data collection equipment, they bounce off an object and come back. And the time is recorded between when that laser pulse is sent and when it comes back, and that time is often used to calculate how far away that object is and other characteristics. Mobile LiDAR data collection is being used more and more frequently, especially to collect traffic assets. And so this is highly accurate and reduces worker exposure to traffic hazards. So there's a picture right here that shows a LiDAR data collection vehicle. So you have all of your collection equipment in your vehicle, and as you drive down the roadway, it is constantly collecting data. UDOT has collected LiDAR data. Manly Communications Incorporated was contracted to collect this data for UDOT, and this began in 2012 and has been updated every 2 years since then. And they have been able to collect over 20 different asset data sets. So we used a lot of these data sets in our research, and all of these data sets and more can be found on UDOT's Open Data Portal, which is an online database. And that's where we got most of our data sets for this research, including AADT, driveways, access category, and speed limit. We also received crash data from UDOT's Traffic and Safety Division, which spans from 2002 to 2014. So we had all this data, and what we wanted to do was try and visualize the data. So we used ArcMap to put our to look at our data and see if we could find hotspots where crashes occur most often, or where locations where there were a lot of driveways on one roadway. And so we were largely looking at crash data, driveway data, raised medians, and access category. And we created a crash density, which puts a specified buffer around each crash point. And as these buffers overlap, you can visualize where more crashes occur on a roadway. We similarly did this with driveway data. We did it two different ways. So the first way we calculated a driveway density was with the use of the line density tool, which did a similar thing with, as our crash data, I guess, density, where it puts a buffer around your driveway, and as these buffers overlap, you can see where there are more driveways on the roadway. We also wanted to look at this linearly, so along the roadway, and so we were able to do that using the spatial join tool. So we compared our crash data, driveway data, and median data, and this was one of the first locations that we looked at, St. George Boulevard in Washington County. So this map compares our two driveway densities with our crash density and our median type. So as you can see, there are a lot of driveways on St. George Boulevard, and a lot of them are close together. However, they implemented or installed a raised median in 2009, I believe, and so that is what shows down here. So that stretches across most of St. George Boulevard. And you can see these are the crashes that occurred after they installed that raised median, and they are largely contained to the intersections. However, sorry, my laser pointer doesn't work on the TV, so I'll be pointing at the screen a lot. But so as you can see right here, the crashes are distributed between the intersections. And this can correlate to the median type at the bottom. It's not a raised median anymore, and so you see a wider spread of crashes. So aside from looking at our crashes and our median types, we wanted to look at our access densities and compare them to the current access category that they're classified as. So as I mentioned earlier, each access category has a recommended number of driveways per mile that should be on the roadway. So we wanted to compare our field calculations, how we calculated our driveway density, and compare that to what our current category was. So we did this for two locations, and I will show you downtown Salt Lake City in this presentation. And we found that there are differences between the two, but we couldn't get a very detailed analysis, and so we decided to use an Excel workbook to try and get a more detailed analysis. So this is the map of downtown Salt Lake City. These two inset maps are color coordinated, so anywhere you see a yellow, that corresponds to an access category 6, or a roadway that should have about 33 to 53 accesses per mile. And so here you can see the difference between our calculated access density from our field characteristics and the access category that it's currently classified as. So the main thing I wanted to point out on this map is this is 400 South, and it is currently classified as an access category 6. However, with the field characteristics, it has more driveways on the roadway than an access category 6 recommends. And so we really wanted to see if we could visualize these differences, but we weren't able to get any more concrete information. And so we decided to use an automated Excel workbook. This workbook was created previously in 2015 BYU safety research. It is programmed in VBA, and it has two different parts to it. So the first is a roadway data portion. You input these roadway characteristic files, and what it does is combine these files into a single Excel spreadsheet and then segments them based on a change in those characteristics. Our second portion of this workbook was crash data. You input these crash data files, and it combines these files into a single Excel spreadsheet. So for each crash that occurred on the roadway, you have all of the information about your vehicle, location, etc. So I made modifications to this workbook. I made modifications to the roadway data portion of this workbook, but the crash data portion remained left untouched because our goal in using this was to get a segmented data file with homogeneous characteristics for each segment. And so I added 4 new data sets to this workbook: access category, medians, driveways, and crash location. And I found that segmenting these data is based on characteristics for all of these data sets was difficult. We found that we had many segments less than 0.5 miles, and we felt that this was going to affect the results of our analysis, and so we wanted to get rid of those short segments and try to eliminate them. So we created 3 adjustments for these short segments. The first was a minimum segment length, which we used 0.5 miles, and what it does is it takes your short segment, and if the AADT is exactly the same as the adjacent AADT segment, then it combined with that segment. And we found that a lot of AADT values for an adjacent segment on the roadway and your short segment didn't match, and so we decided to do a 10% AADT buffer. So if your adjacent segment had an AADT within 10% of your short segment, then it was combined with that adjacent segment. But we did still find segments that were less than 1/10 of a mile after both of these buffers, and so we decided to automatically combine them with an adjacent segment to eliminate all segments less than 1/10 of a mile. And we felt that segments less than 1/10 of a mile adding these to an adjacent segment would not affect the homogeneous characteristics of the segment. Oh, and this is a figure showing the segments less than 1/10 of a mile after each buffer was implemented. So you can see our minimum segment length buffer of 0.5 miles was very effective in reducing segments less than 1/10 of a mile, and we were able to eliminate those completely with our final buffer. So using the output from our automated Excel workbook, we wanted to look again at our field characteristics, how many driveways were on our roadway compared to what the access category that the roadway was currently classified as recommended. And so we did these for 2 different characteristics of access category. So we looked at access density, again, how many driveways are on that roadway compared to how the access category is working or recommends. And we also looked at speed limit. Is the speed limit higher or lower than the recommended value for that access category? And then we combined those and looked at segments where both they had more access than recommended and the speed was different than recommended. And so we did find differences, but it really just simply means that there is a difference between our category and our field characteristics. So there needs to be more research to identify how we can, whether segments need to be placed into a new category or changes need to be made to the roadway, such as driveway consolidation, because other treatments may be helping our segment act as its current access category, even though it has more driveways on the roadway. Okay, so this is a table depicting our segments that we found that had more access per mile than our recommended access category from the R930-6. So looking at access category 5, there are 313 total roadway segments that are categorized currently as an access category 5, but 119 of those have more access on them than an access category 5 warrants, which is 33 accesses per mile. So all of these segments have more access than recommended. So this is a similar thing, just a way to visualize it. This is zoomed into Salt Lake County. The blue lines represent the segments where there are more access than our current access category recommends. And so Redwood Road and State Street right here, much of those roadways show that there are more access on those roadways than recommended. So we wanted to do an analysis that would look at how these segments with more access per mile fit into an access category. Do they fit better into a different access category? And so we decided to place segments into a new access category based on their field characteristics. There is a maximum recommended access density of about 73 accesses per mile. And so if any segment had over 73 accesses per mile, we automatically moved it to an access category 9, which is entitled Other. We felt that was the best place to put these segments. So we did this two different ways. First, using urban code and access density, and next using urban code access density and speed limit. So again, looking at access category 5, we have 193 segments that stay in access category 5 based on their current characteristics. However, 53 of those are moved to an access category 6 based on their urban code and how many accesses there are per mile. So when we add speed limit into our criteria, we see that there are 109 segments that stay in access category 5 and 120 segments that are moved to an access category 6. And so we see that there are a lot more segments moved into other categories when we add speed limit into the mix, because it's another criteria that it has to match for our access category to be the same. So in this analysis, we found that we focused on whether the access density compared to how the access density compared to the current access category. And going back to our downtown Salt Lake map, where we saw that the current access category is a 6, but it's acting as an access category 8, meaning it has more accesses per mile than an access category 6 recommends. That roadway actually has a raised median on it. And so we were interested to see how raised medians affect safety and decrease crashes on the roadway. And so we decided to run a before-after analysis on raised medians. It is a hierarchical Bayesian multiple linear regression analysis. And this was created in previous research in 2010, and we modified it to fit the scope of this project. So we found 20 raised median segments in Utah where the raised median was installed between 2002 and 2014. And we found, we wanted to see how safety was affected on these roadways. And so this is a picture of a portion of our input data. We broke each segment up by year, and so we have whether the segment and the year was before the raised median was installed or after. And we also have the access category of the roadway, the number of crashes that occur each year. And so we input this data into our model, and found that the best model that we found only had 3 covariates. So that it was whether the segment and year was before or after the raised median installation. We had VMT and VMT squared, or vehicle miles traveled. And we used VMT instead of AEDT because it gave us a better model. We ran the model based on access category. So of our 20 raised median segments, there were 3 access categories that were shown, access category 3, 5, and 6. And we also ran the model with different severity groupings. We wanted to see how does raised medians reduce crashes with a severity 4 or 5, where you have fatalities and incapacitating injuries. So the results of our model, we received these regression plots from our models. We were able to look and see where raised medians decrease crashes on a roadway. So for example, between about 18,000 and 24,000 VMT, we see that crashes are reduced. However, due to not enough data in certain areas, our confidence intervals, which are our 95% confidence intervals, are very wide because we don't have very much data. And so we cannot make any specific inferences that raised medians reduce crashes here because of that. So we see a similar plot looking at just severities 1 and 2, and 1, 2, and 3. However, when looking at more severe crashes, we cannot make any specific inferences because our 95% confidence intervals are very wide. So as part of this before-after analysis, we looked at crash modification factors, and we plotted these factors. So for any given VMT, we have a CMF that we can coordinate with that. However, although you see a lot of variation in these plots, our y-axes are actually very small and varied by 1,000. And so in reality, these are our more severe plots. So these are our mean CMF values from those crash modification factor plots. And from these CMF values, we can predict the number of crashes we expect to occur after a raised median is installed. So we'll use access category 3, severity 4 and 5 as an example. So if we had 100 crashes occur on a roadway of severity 4 and 5 before a raised median was installed, then we multiply that by our 0.46 crash modification factor to receive 46 crashes. So this is the number of crashes we predict will occur after the installation of a raised median. We were also able to find crash reduction factors, which is just 1 minus your CMF factor multiplied by 100. And so we were able to see a 64% reduction in crashes. You have your 100 crashes that happened before the raised median, 46 that occurred after. So you have a percent reduction in crashes of 64. So overall, I have used the LiDAR data to evaluate driveway and access using the existing access management guidelines in R930-6. I've been able to do an analysis based on field observations, and even though we found differences between the current access category and the current characteristics of the roadway, it simply means that there is a difference. We cannot say anything further. Further research would need to be conducted to see whether the roadway segment needs a new access category assigned to it, or if driveway consolidation needs to happen, or other access management treatments to help with that. So the roadways may need to grow into the criteria, or changes may need to be made to the access category. I also did a before-after model on raised medians to see how raised medians reduce crashes and improve safety on a roadway. And we see that for all access categories and all crash severity groups, that there is a reduction. And generally the reduction is greater for severe crashes of type 4 and 5 than for the other severity groups. So overall, my contributions to the current access management literature include exploring the usefulness of LiDAR data. I have been able to complete a system-wide access category analysis of Utah state routes and compare the current access categories with the field data. And I have been able to identify segments that can be looked at further to see what problems may need to be fixed on those roadways. I also ran a before-after analysis on raised medians. And though this has been done before, my analysis is different because we have so much more data because of our LiDAR data collection that UDOT has performed. And we are also able to run more segments in our model than the previous research. And finally, we also analyzed our results by access category, which has not been done before. So thank you for coming. I really appreciate your support, and I hope you enjoyed it. Thank you.
All right.